Hi. So in the last lecture, remember, we dealt with quantum particles, and we talked about how quantum particles have wave-particle duality. So that means that they can be modeled as waves or particles depending upon what your situation is, what effect you're trying to model. Now, since they're sort of localized in space, as opposed to an ideal wave, which is infinite in extent, then that means they have to travel as a wave packet. Remember that we talked about the idea that as a wave packet becomes confined to a limited region in space, delta x, that it takes a larger range of wavelengths or wave numbers to create that packet, delta k. And as the packet's duration in time is narrowed, delta t, then the number of frequencies that makes that group also gets larger. And this could be expressed as a ratio. Delta x, delta k is approximately 1, and delta t times delta omega is also approximately 1. And this led to the idea behind the Heisenberg uncertainty principle. Now, this is a picture of Werner Heisenberg. He was a German physicist who developed matrix mechanics, or sort of a matrix approach to quantum mechanics. And the matrix approach and Schrödinger's approach were later shown to be equivalent. And his many contributions to modern physics include the uncertainty principle, which we're going to talk about today, for which he received the Nobel Prize in 1932. And also some work on two forms of molecular hydrogen and theoretical models of the nucleus. But today, we want to talk about his work on the uncertainty principle. Now, in classical mechanics, it's possible in principle to make measurements with arbitrarily small uncertainty. But quantum theory predicts that it's fundamentally impossible to make simultaneous measurements of a particle's position and momentum with infinite accuracy. And this is a consequence of the fact that these particles are waves, and they are wave packets. So this is a very different idea from the uncertainties that you might have learned about in classical physics or your intro physics labs. The uncertainty that I'm talking about here isn't due to the least count in your measuring device or the precision or accuracy of your measuring device. It's not due to that. This is a fundamental uncertainty, okay, in the particle's position. And it's also not the same kind of uncertainty or spread in the data that you might think of when you're thinking of classical models, like the Maxwell-Boltzmann model of an ideal gas. There you talk about the statistics and the spread in the data just because there's so many particles there that you'd need a huge supercomputer in order to track each and every one of them and talk about the speeds and positions at any given time of any particular particle. However, if you had such a computer, you could do it, okay? So you could model an ideal gas, for example, and then you can talk and track about the motion of each individual particle and its position and momentum exactly at any given time. So that's also not what I'm talking about here. It's not because there's a lot of particles that we need to use these statistics to describe them. It's because these particles fundamentally have an uncertainty associated with them because they are quantum particles. So that's what I'm talking about here. So the Heisenberg uncertainty principle tells us that it's physically impossible to measure simultaneously the exact position and exact momentum of a particle. And these inescapable uncertainties don't arise from imperfections in practical measuring instruments. The uncertainties arise from the quantum structure of matter and its wave nature. The fact that these particles are really wave packets, and they have a spread in their wave numbers that is proportional to the spread in their positions. So, it's impossible to measure simultaneously with no uncertainty the precise values for k and x for the same particle. Remember that our wave number, k, is 2 pi over lambda, and lambda is h over p, and so k can be related to p. K is equal to p over h. P over h bar, I'm sorry. And for the case of a Gaussian wave packet, which is a specially shaped wave packet that I'll talk about in just a second, then we have the uncertainty principle, delta k, delta x, is equal to delta p times delta x over h bar, which is equal to 1/2. Okay? So, thus for a single particle, we have Heisenberg's uncertainty principle. Delta p, delta x is greater than or equal to h bar over 2. So that's the famous uncertainty principle that we've been leading up to all this time. Now, the inequality there is because the Gaussian wave packet represents the minimum possible uncertainty, and all other wave packets have larger values. In fact, in some of the problems that you might work for homework, you might have to estimate delta p times delta x is proportional to h bar, and not h bar over 2. Now, a Gaussian function looks like this. It's the bell curve or normal curve that you might have heard about in one of your statistics classes. So a Gaussian function is when you have your exponential here, e, proportional to some constants times negative x squared. Okay, so that's a Gaussian shape. And so basically that's what we're saying, that this particular shape wave packet gives you the minimum possible uncertainty in the Heisenberg uncertainty relationships. And that's where the greater than or equal to h bar over 2 comes from, because all other wave packets will have a larger uncertainty than the Gaussian. Now I gave you the delta x delta p is greater than or equal to h bar over 2, but remember I also talked about the spread in time being proportional to the spread in the angular frequencies. Delta t delta omega is proportional to 1. So if you plug that in, then basically 2 pi delta t times delta f is approximately 1. And then if you plug in for what the energy would be, then remember E is equal to hf. So if you multiply both sides of that equation by h, then you have 2 pi h delta t. Delta f is proportional to h. And then that gives you your energy time uncertainty principle. Delta t times delta E is proportional to h over 2 pi, which is h bar. So this is another form of the energy principle that can be expressed in terms of energy and time. So you have two, your position and momentum one and your energy time one. So the energy time uncertainty principle can be stated, delta E, delta T is greater than or equal to h bar over 2. Yet again, the h bar over 2 and the greater than or equal to part comes when you have that Gaussian wave packet setting your minimum possible uncertainty. Now this actually suggests that energy conservation can appear to be violated by an amount delta E as long as it's only for a little tiny time interval as dictated by the energy time uncertainty principle delta T. And we'll do an example of that in a little bit. So that brings me to another classical analog for these concepts, and that's the idea of bandwidth. So if you've taken electronics classes, or if you're an aficionado of shortwave radio or whatever, you might have heard of bandwidth. So remember FM radio stations. FM means frequency modulated. So basically when you're listening to an FM station, what's happening is someone's speaking into a microphone, and then that is converted to an electrical image of the sound that's formed by the microphone. Now the radio station that you're listening to, say 98.7 FM or whatever, they have a carrier wave, and that carrier wave is generated at a transmitter at a very specific frequency that you tune into on your dial. But then what happens is the electrical image of the sound formed by the microphone modulates that carrier wave frequency. And so it comes out being modulated, kind of like the cartoon here on the right, where the frequency does seem to vary a little bit as you look across that cartoon. All right? Now, there's limits to how far you can modulate the frequency, and that gives you your signal, the bandwidth. And bandwidths are assigned for all kinds of broadcast communications, and they impose a delta F and hence a delta T. If they didn't do this bandwidth thing, then what would happen is 98.7 FM would overlap with 98.9 FM too much, and you get too much static in your signal, so they restrict it. Now for FM radio stations, there's about a 200 kilohertz bandwidth, and it runs, the carrier waves run from 88.1 to 108.1 megahertz for 100 possible bands. And then for AM, you have a 10 kilohertz bandwidth from 540 to 1600 kilohertz for 106 possible bands. So that's your two bandwidths there, okay? And anytime you impose a bandwidth, delta F, it also imposes an uncertainty delta T. So yet again, this is kind of a classical analog to the uncertainty principle. Okay, let me do an example problem for you. And this gets back and sort of hints at some stuff that we're going to do in later chapters when we cover the quantum harmonic oscillator when we're doing our introduction to quantum mechanics. So here's the problem. Show that the minimum energy of a simple harmonic oscillator is h bar omega over 2. What's the minimum energy in joules then for a mass of 50 grams oscillating on a spring with a spring constant of 12 newtons per meter? All right. So note here that the example problem asks you basically about a classical oscillator. And this is to highlight that this h bar omega over 2 is going to be really tiny. And so in classical physics, you wouldn't expect to see it. Okay, so here's the solution. Remember that from introductory physics that the mechanical energy, E, is equal to K plus U, where K is the kinetic energy and U is the potential energy. Now for a simple harmonic oscillator, remember that your potential energy is 1/2 kx squared, where K is the spring constant of your spring. And the kinetic energy, of course, can be expressed as p squared over 2m. So for a quantum particle, we can't set the mechanical energy equal to 0, because that would imply that p and x are both 0, and we can't simultaneously know p and x exactly. We just can't, okay? So what that means is that our minimum energy is going to be dictated by the uncertainty principle. So remembering that the mechanical energy is the sum of the potential plus the kinetic, that means our minimum energy, E min, would be equal to 1/2 k times delta x squared plus delta p squared over 2m. Now the average contribution of the potential and the kinetic energies really should be the same, okay? So that means that we can set k delta x squared is equal to delta p squared over m, and that's equal to our minimum energy. So if we solve this, we set k delta x squared equals delta p squared over m, and we solve, then we can solve delta p is equal to delta x times the square root of km. Now, the minimum values of the uncertainties are known from that Heisenberg uncertainty principle. Delta x, delta p is greater than or equal to h bar over 2. So if I plug in for delta p, then I get delta x times the square root of km times delta x again is greater than or equal to h bar over 2. And solving, that gives me delta x squared is equal to h bar over, or greater than or equal to h bar over 2 times the square root of km. Now, if I look at this, this means that the E min, the minimum energy, is equal to k delta x squared, which is greater than or equal to h bar k over 2 square root of km, okay? Because I'm multiplying what I got for the delta x squared in the previous slide times k. When I solve for this, I get h bar over 2 times the square root of k over m. Well, if you remember your introductory physics class, then you remember that the angular frequency omega for a simple harmonic oscillator is equal to the square root of the spring constant divided by the mass, root k over m. So now I can plug in for root k over m into omega, and I end up with h bar omega over 2. And that's my minimum energy. It's got to be greater than or equal to that. So I'm done. I proved it. Now, if I want to plug in the values from the question, I plug in 50 grams or 0.05 kilograms, and K is equal to 12 newtons per meter. Plugging that in, then I find a number of 8.2 times 10 to the minus 34 joules. 10 to the minus 34 joules. That's super tiny. So it's not surprising that we don't notice that the minimum energy of a classical oscillator isn't 0, right? Because we can't detect it. We can't see it. It's too small. Now I want to discuss a couple applications of the Heisenberg uncertainty principle to cool things. So one of those is applying the uncertainty principle to unstable particles. Now it turns out that many of the particles discovered in high energy experiments have extremely short lifetimes. And what that means is that they decay into other products, okay? More stable products. Now, according to the uncertainty principle, this means that we can't know their rest mass energy to a high precision, because delta E, delta T is greater than or equal to h bar over 2. So if delta T is really short, then delta E is going to be considerable. So for example, pi mesons, J psi, and upsilon particles, they have mean lifetimes of 8.4 times 10 to the minus 17 seconds, really super short, 7.1 times 10 to the minus 21 seconds, and 1.2 times 10 to the minus 20 seconds, respectively. So if you were to measure the mass energy of those particles, then you'd see plots with a distribution called a Bright-Wigner or a Lorentzian shape. And here, gamma is the full width half max of this curve. So this is the shape I'm talking about, this Lorentzian line shape. Now often the uncertainty in the energy is therefore estimated as half of the full width half max, or gamma over 2. And this is taking a statistical view of the uncertainty, really, because if you think about it, then what we've done is we've measured the mass for a whole bunch of these types of particles and just gotten a distribution of what those looks like and plotted them out, okay? If you were to look at each individual particle, the energy time uncertainty principle would of course apply. But looking at them as a whole, we can see what the energy time uncertainty principle predicts here for the uncertainty in the energy, and that's the full width half max of the curve there. Okay, so sometimes when you're doing this, the lifetime tau of a particle is measured directly and used to estimate that full width half max gamma. And others, gamma is measured and used to estimate the lifetime. But either way, the uncertainty principle has to be obeyed. gamma over 2 times tau has got to be greater than or equal to h bar over 2. So you might see some physics problems like that popping up in your homework. But I'd like to do a slightly more interesting problem as an example. This one comes from Crane's Modern Physics. A proton or a neutron can sometimes violate conservation of energy by emitting and then reabsorbing a pi meson, which has a mass of 135 MeV per c squared. Now to break for just a second here, this is the idea of an exchange particle. Basically what this is coming from is that the nuclear force, which binds all nucleons together inside of the nucleus, strong enough to overcome the repulsive Coulomb force between protons. This force, and indeed all forces, are mediated by an exchange particle. Okay? So the idea is that the proton and the proton sit next to one another and they exchange these pi mesons back and forth saying, I'm here, be attracted to me. I'm here, be attracted to me. Right? Now these pi mesons have a certain range, and we're going to talk about what that range is estimated to be based upon the energy time uncertainty principle. Okay, now I'll continue with the question. So the mass of the pi meson is about 135 MeV per c squared. And this is possible as long as the pi meson is reabsorbed within a short enough time delta t, consistent with the uncertainty principle. So what I'm talking about here, what I'm talking about with an exchange particle, is let's say the proton is sitting next to another proton or another neutron. And then that proton generates a pion or pi meson and gives it to that neighboring proton to tell it it's here and that it should be attracted to it. So for the brief amount of time, right, that pi meson exists and it's transmitted in between. Then the other proton picks it up and it disappears again. So this is the idea of the exchange particle. What that means is that the lifetime of that pi meson is dictated by the energy time uncertainty principle, because you can only violate conservation of energy for very brief times. So, by what amount delta E is the energy conservation violated? And for how long a time delta T can that pi meson exist? And then, assuming that it travels close to the speed of light, what's the range of the pi meson particle? Okay, so the rest mass energy of that pi meson, 135 MeV, that's the amount that it would violate conservation of energy there, right? Because it's got to wink into existence, travel across that really short distance in a very brief time, and then wink back out of existence when that proton takes it. Okay? So that's the amount of energy, 135 MeV. If we take that and we plug it into the uncertainty principle, and here I'm going to use the idea that delta E delta T is proportional to h bar, so I'm not taking the minimum possible value. Okay? So there, a delta T would be h bar over 135 MeV. Remember, h is 4.136 times 10 to the minus 15 eV seconds. Okay? So then you would divide that by 2 pi and then divide that by 135 million eV. When you do that, you end up with 5 times 10 to the minus 24 seconds. So that's the amount of time that energy conservation can be violated for. And that's the amount of time that that pi meson is allowed to exist. Now, assuming that it travels close to the speed of light, 3 times 10 to the 8th meters per second, then you can estimate the range by multiplying the speed times the time that it's allowed to exist, c delta t. When you do that, you get 1.5 times 10 to the minus 15 meters. And that's approximately the size of a nucleus, okay? So you're not going to get really huge nuclei, right? You're not going to get really huge nuclei, because the range of the strong force, the range of that nuclear force, isn't large enough, because that way you can't violate the energy time uncertainty principle for that long. Okay, so there you go. I hope that blew your mind just a little bit, and I'll see you in class.